summer series, Lunch and Learn series. Today we're looking at the Model 577, which is a flagship pulse and delay generator. And I have a special guest today, Steve Birell, who is the Chief Engineer and Product Designer of the 577. And we're going to go through some of the features and options that make this product a very unique and standout instrument for Berkeley Nucleonics. Quick couple of comments before we get started. This is a brief webinar, but we will record the webinar and provide a link to anybody who registered or anybody who wants to review at a later time. We'll have a quick opportunity for some Q&A at the end of the webinar. There's a chat box in the window. If you maximize your window, you'll probably have the best experience. And if you have any questions, you can drop them in the chat box. And that is not private, but we'll try to get to all of those. The presentation is not classified and can be certainly shared with colleagues of yours as well. Berkeley Nucleonics has a long history in signal generation. We started in the early 60s, a spin out from the Lawrence Berkeley National Lab, and we've been providing pulse and delay generators now for over 50 years. One of the sort of key attributes to our products is low jitter, and we always try to meet the toughest timing requirements in the industry. And with the Model 577, I think we do a great job. Quick touch on our rep network. We do have distributors and sales reps all around the world. These are people that can take your orders, service your products, handle repairs, technical questions as well. They can provide some translation if you need localized language materials and support. And you could quickly jump on our website or give us a call or an email, and we'll put you in touch with the partners of ours that would close to in your region. So, welcome, Steve.
Hi.
Yep.
Glad to be here.
Great. So we're talking today about the 577. I did grab one just to give perspective here. This is the 577. Oops. And you see it there on the screen as well. It's about 6 pounds, very light, handy product with a handle for carrying it around the lab. Some of the important specs of the 577 are the delay and width resolution of 250 picoseconds and the low jitter of the 50 picosecond channel-to-channel jitter. And also, the very wide pulse widths. So some high-performance delay generators have low jitter, but you also can't set very wide pulses. And in this case, we provide that the very wide pulse widths too. And most importantly, which we're going to go deep into today, is the flexible ordering options. The instrument is set up with many features and options that allow you to customize your product to your needs. A quick look at the front panel. This is an 8-channel unit with a gate and trigger connector at the bottom. And you see there A and B. The way it's designed is every 2 channels is considered a channel bank. So you can actually customize each set of 2 channels on your product. So A and B can be customized and different from C and D, E and F, G and H. You see the blue keys here. I can actually, let me turn on a marker here. Oops. So these blue keys right here are soft keys, and the menu options for those change depending on what menu you're on. The Smart Encoder is this guy right here. And this is very useful for adjusting through scaling through different settings and parameters quickly. And then what's unique also, we have a run stop button here, which is different from the power button. And then there's a third power button on the rear panel as well. Steve, is there any having a run stop button is a little bit unusual when you have a power button as well. Is that correct?
Yeah, some of the instruments can use the power button as a run stop, and that can be confusing sometimes. If you hold the button down long enough, then it will turn off, and the run stop allows, prevents that. Yeah.
Okay. And then the gate and trigger are down at the bottom, and we're going to talk a little bit about those connectors as well, because those can be customized.
Yeah, one thing to note is on the soft keys and the overall architecture of the system with the flexible channel banks and stuff is that it's very easy to not only provide the standard custom options, but if the users have a specific function they need that's not provided, there's a possibility that BNC can provide a engineered unit specifically for an application, and it's very easy to add it to the menus with the way that they're set up.
Yeah, I have a pic. I'll put this up to the camera. Oops, that's not working. Got a problem with my background here, but you can't see the display. Here are the soft keys, and then you can see right here, this is the kind of where the language nomenclature sits. So I threw up a test department background. My office is really boring, Steve. And so I've got a photo of our test lab here, and I threw that in the back just to kind of add a little, make it feel like we're, back in the lab. It's with everybody working remote these days, it's a little boring. All right, let's look at the rear panel. Good. So this is your traditional. You want to run through the rear panel then, Steve?
Yeah. So we have a clock in and clock out, which allows the users to provide their own reference clock for the unit. This allows you to lock it into other units, and then the out allows you to daisy chain it. So theoretically, you could lock any number of systems together, and that reduces the external jitter, provides a much more stable output. The USB and the RS-232 are our standard outputs, communication outputs, and then optionally we provide GPIB and Ethernet. So the unit can be fully controlled via the computer interface. There's a relatively straightforward command set that allows you to control all the same functions as you do from the front panel. And you can use the front panel at the same time. So the way the system is set up, if you wanted to, it'd be a little bit confusing maybe, but all the channels or all the inputs are independent. So you can be controlling it via the USB and the RS2 simultaneously. Just trying to keep track of what state the instrument in might become a challenge, but the instrument is very flexible that way. And then we have the power entry module up here at the top, and that allows 100 to 240 volts, 50 to 60 hertz. So it's basically internationally compatible with any voltage supplies anywhere, and that's integrated with the power switch. Also, you'll note here we do have a fan in the system, keeps the system nice and cool and makes it reliable. So.
Yep. And the handle is adjustable too. It can be used as a stand or as a handle or as protection for the front panel. So in this picture, the handle's up above, but if you swivel that around to the bottom, it just pivots the screen up so you can see the screen better when you're working at your bench. And if you pivot it halfway, it provides some protection for the front panel for, say, in transit. Okay. Now we're going to look at some of the special options that are a little bit unique to the 577. And the first one is the high voltage option that we call it AT45.
So just a moment about just the options in general. As David mentioned, we have banks of 2 channels each, and each of the banks is a separate card, so that you can load in the unit up to 4 banks, 8 channels, and each bank can be a different module. So when we talk about these modules, you can visualize having a unit that may have one or two AT45 modules, and then maybe a standard TTL module combined, so that you can have a unit that provides specifically what you need for your application, and it provides a lot of flexibility in terms of how you configure the units. These modules are factory installed, so they're not user changeable, but you can order them however you wish. This is an example of a high voltage module, puts out up to a 45 volt pulse, originally designed for some specific applications that required a higher voltage that was a little more immune to noise and whatnot. It required a reasonably high fast rise time. So we have a low Z mode, which gives you a 2 nanosecond rise time and a 2 nanosecond fall time. So the circuit is a bit of a challenge, particularly on the fall time side, to implement. But you can see the waveforms that we've done a pretty good job of avoiding too much ringing. There's a little bit of ringing on the low Z side, but not a lot compared to how fast we're transitioning the pulse. Because of the power requirements of this particular module, the units can only have 2 banks with an AT45 installed. So if you have an 8-channel unit, only 2 of the banks can be, or 4 channels can be AT45. The rest have to be some other module. But otherwise, there's some limits with this module. As you can see, the frequency is limited to 100 kilohertz. But other than that, it's fully programmable, 4 volts to 45 volts, and higher, low Z modes. So yeah.
And then if you, I forgot to mention this, Steve, but on the left side of the black bar, there's that little pencil, and if you click on the pencil, you can go up and turn on your marker. So if you want to show certain, like the ringing, for example, it's right here that Steve was referencing. If you hold the button, it'll create. Yeah, there you go. But it is great. It is good. That's a very clean signal considering the transitions. This is an option. So if you have AT45 on channel 1 and 2, you can also turn it off, right, and just stick with your TTL outputs on channel 1 and 2 and get So it's
so pretty much. I think most of the modules, except for the light modules, typically have 2 functions, and typically one of them would be the standard TTL CMOS or the adjustable option, one of those 2. And so when we talk about an AT45 module with these special parameters, it also has another mode that provides the adjustable standard output, as we'll see later on, the specs for that.
Good. Okay. All right, let me switch to the next slide here. We could talk a little about the matching.
So these modules are designed for more demanding. The TZ50 and the TZ35 are designed with faster rise times, and designed to be impedance matched to 50 ohm loads to minimize the ringing and other problems associated with mismatched impedances. So you can see that we have TTL CMOS mode, and the impedance matched to the 50 ohms limits the output to 4 volts typical. But the rise time is good. Adjustable mode is the same as the standard option, which is adjustable up to, I think, 10 volts.
10 volts, yeah.
Yeah, okay. And then the TZ35 is a high voltage equivalent. It goes up to 35 volts. And then the AT35 is a standard 35 volt module. So you have the rise time of 30 nanoseconds versus more like a 3 nanosecond when you're in the TZ mode. And again, it's designed for 50 ohm is, again, limited to 200 hertz in this case. Other things of interest.
Okay. What one of our visitors is saying your mic is a little further from your mouth than mine, so if you could move your mic a little closer, that'd be great. What would be how's that, Joe? Does that sound better?
Try again. Testing.
He says, great. Thank you, Joe. Good man. So what are some, just off the top of your head, Steve, applications for the higher voltage? And I see the AT35, we can go all 8 channels, which is nice. Do you have applications that come to the top of your mind with where these, the TZ50 and AT35?
There's the applications that we're aware of are ignition devices for testing explosive devices, things like that, using the pulse generator in those areas. They've standardized for their triggering process on higher voltages, again, for noise immunity and whatnot. So, and this could be anything from airbag igniters to missiles and bomb type testing,
yeah.
things like that.
Yeah.
But there's a sort of a niche pyrotechnic industry that likes to use these higher voltages just for safety reasons as much as anything, I guess.
For driving lasers, the TTL is typically sufficient?
Typically, yeah. We do occasionally require a fiber coupled triggers, which we have a module for that as well. I think we'll talk about later.
Okay.
But yeah, most lasers are quite happy with the TTL CMOS. That's pretty much a standard in the laser business, I think.
Okay. Moving along. So here is the optical inputs and outputs using LEDs. I have a photograph of these too, by the way. Let me jump over here. So here you see, this is a little bit older unit, but here we have the BNC connectors on the front panel are swapped out for these ST front panel connectors. You see the BNC connector is on the gate connector here, but then this is a ST connector without a cap, and this black thing here is just a little cap that protects the connector from dust getting in. So here's where your fiber optic cables will either where you'll get your signals out from the pulse generator, or you'll use an optical signal in to trigger or gate the connector.
Right, and these are based on standard modules, and quite often they're used to trigger devices in really noisy environments. It allows you to run your trigger cable, past noisy modules and noisy environments, and run them a reasonable amount of distance. You can see a maximum distance of 1.5 kilometers. They're based on standard modules, so they can interface to any number of other devices that have the same standard interface. And again, you can put, only one bank needs to be these, or you can have all 4 banks can be optical outputs. All depends on what the user's needs are.
You mentioned large capacitor banks, like big rooms full of capacitors that typically create a lot of noise, and the optical isolation would be ideal. Exactly.
We know that people use them as an input device to trigger the pulse generator. They'll use the optical inputs, and this was in a huge capacitor bank. We're talking it's about, the capacitor itself is a 12-foot diameter cylinder, about 10 to 15 feet long. You can actually walk inside it. And so the voltage in there, I think, is 35,000 volts or something like that. And it's triggered by generating a spark gap in the middle of the thing. And obviously you don't want that going off until you're ready, because it's a huge amount of energy that's released. And the goal is to produce high energy X-rays. So all this, once the capacitor bank is triggered, all the current goes and blasts the titanium shield, which generates these X-rays. So obviously you don't want that going off until you're really, really ready for it to go off. And so they found that the most reliable triggering method is to have the trigger come in as an optical fiber, and then they can put the actual pulse generator in a EMI shielded rack, and then everything works out really good. As far as I know, they've never had a false trigger in that environment, so it's worked out pretty good.
Okay. Dual trigger option.
So this is something that we came up for these high-end products, is to add a second trigger input. It's normally called a gate. So on the panel, we have a trigger input and a gate input, and it separates those two functions out so that you can, for like in a laser application, you can use the gate input with an interlock on the door to disable the laser if someone walks in, and still have a trigger input available for triggering the pulse generator. But the one feature that we added was that you can also use that gate input as a second trigger. And each channel can be assigned to either one of those inputs to be gated and or triggered by that input. So for example, if you had a laser system that needed the diodes to be stabilized, and they were really high energy devices. I remember one application years ago where it was a high energy Alexandrite system, and if you stop firing the laser without sort of doing a ramp down, you could potentially damage the system. And so you could set it up so that channel 1 was the diode trigger, and it was continuous no matter what. And channel 2 was the Q switch trigger, and it was gated by one of the inputs, such that when someone came in the door and you needed to have an interlock shut the laser off, it would not shut the diodes off, but it would shut the Q switch off and stop the lasing action. And if the trigger was being provided by a trigger input, you could still have the other channel be gated by the gated input. So there's a lot of flexibility in terms of how you configure it, and every channel, as I mentioned, is independently assigned to either of those inputs and can independently be triggered or gated. So you could have one channel that's triggered off the rising edge of a pulse, and another channel that's being gated by the pulse width of the same pulse on that channel. So a lot of flexibility in terms of controlling, putting the pulse generator in a safe environment where you can use interlocks to control things, as well as trigger signals to control the timing of things.
Yeah, Steve, I know we've been working on pulse generators for a long time, and I'd have to say I don't know that there's a pulse signal requirement that you haven't tackled, whether it bursts and nested bursts and divide by ends and duty cycle control and multiple triggering off of other pulses and triggering off of leading and falling edges. And I think that the 577 is a culmination of a lot of good hard years of experience and a lot of requests outside the conventional pulse generator requirements. So I think the next slide's going to speak to why you're able to have such a flexible solution. Slide after that. This is kind of a boring slide. This is I'll cover this one. This is the extra 2 ports. So the standard product comes with the USB and the RS-232. And we give you a free software utility that lets you set each channel up the way you want on a computer, or you can use Skippy commands to run your box. But then with the COM option, we add a couple more ports on the rear panel. No power over Ethernet, just commands over Ethernet. Is that right?
That's right.
Yeah. Any other things? I mean, I know GPIB is. We keep thinking it's obsolete, but people keep using it.
People keep buying it.
Yeah. So we'll keep making it. Anything further on those two?
I don't think so.
Yeah. Okay.
That's good.
Good. And then this is kind of a really nice, simple representation of what's going on under the hood.
There you go.
Tell us what's going on here.
Yeah, as David mentioned, this unit represents a lot of experience over the years, and a lot of that experience was gathered by customer requests for how to do this or how to do that, and wanting to do things that maybe we couldn't do years ago. As David mentioned at the beginning, what this whole line of pulse generators was conceived of as based on a digital platform, and one of the reasons was to be able to provide a lot of flexibility in the generation of the pulses. And so what we came up with over the years is an architecture that's we hope is relatively simple to understand. One of the challenges with providing a large number of ways of configuring the system to generate pulses is that it can get very, very complicated very quickly. And so to try to mitigate that and provide a simpler user interface, we've divided up into two parts, two for the logic functions. The first part is this system mode generator, and it basically generates what internally we call a T0 pulse, or the system pulse, and that's the running at the rate that you specify for whatever frequency you're dealing with. All this module provides the ability to put out a constant set of pulses, or a single shot burst mode or duty cycle function. It started by, how do we clear this?
Oh, you just do their back, use the little back arrow to undo.
Oh, okay.
I can do it for you if you like.
Go for it. Okay. Whoop.
Okay. Oh no, I'm sorry. The back arrow in the back arrow on the left pane there. You see the fourth one up from the bottom.
Oh, I see. Gotcha.
I'll let you. There you go.
All right.
We're about solving problems, right, Steve?
That's right.
Yeah.
So the way this module works is you end up with you start with a start pulse over here that can be provided by the software start from the front panel or from the communication ports, or it can be a gate or trigger input from the hardware inputs. That starts this timer going, and if it's in continuous mode, it will just start to continuously generate pulses at whatever frequency the user defines. If it's in a burst mode, it'll generate a burst of pulses, again at the frequency and number that the user defines. And then that module will then generate its own start pulse, which is called T0, and that goes to the channel modules over here, and they're very, very similar to the system module in the sense that they have all the same functions. They have the single shot mode, they have the continuous mode, burst mode, and duty cycle mode, and they're started by a start signal, same as the start signal over here, except it comes from the T0 pulse. In addition, we have the gate inputs and the ARM input that can control each individual channel. So as mentioned earlier, I can gate one channel and then let the other channels be free running if I want. So I can have the system mode over here, say, put out 100 pulses in a burst mode, and then those will come over here, and if the channel's in continuous mode, it'll put out the same 100 pulses because it's only going to put out a pulse every time it sees a start pulse coming from the system mode. if I put this in a channel in duty cycle mode, say 10 pulses on and 10 pulses off, then I'll get 100 pulses from my system mode, and I'll generate 50 pulses. I'll generate 10 on, and then I won't generate pulses for 10 inputs, and then I'll generate 10 more. So the net effect is I'll do 10 on, 10 off, and I'll generate a total of 50 pulses to the 100 pulses that came in. And then to further add to the ability to generate complex waveforms, we take the output of each of the timers that's in here, and we go through an output mux that is for every output channel. So like channel A up here has an output mux, which can take the output of any of the timers. So the default is channel A is assigned to timer A, and channel B is assigned to timer B. But I can, if I wanted to, I could just swap those. I can make channel A be assigned to timer B. That's not much excitement there.
But maybe A, B, and C all assigned to channel A, for example.
Exactly. I can mux them all together, and basically what the output mux is an OR function, and so that allows me to make like a double pulse situation. If I have channel A putting out a pulse, and then I have channel B putting out a delayed pulse, and I OR those together, I can have I have a period of 100 milliseconds, and I have the first pulse is 1 millisecond on channel A, and channel B has a delay of 5 milliseconds, and then it puts out a 1 millisecond pulse. Then I'll end up with a double pulse that's in a 5-7 millisecond window every 100 milliseconds. So it'll be useful for PVI applications where you're double pulsing a laser or something like that. But it allows you to do rather complex things, because I can mux all 8 channels into one output, and I can change the pulse width. I can change the relative frequency. I can do a lot of various things with that. So the combination of using your system mode and then your channel modes, the different modes in each one of those gives me a lot of flexibility, and then adding that to the output muxes completes the whole thing. So it's very rare that we get a customer that has some sort of pulse train that he wants to generate that we can't figure out a way of generating that output. And we certainly encourage customers to inquire from our BNC service group as to if they're struggling with a complex waveform, how to generate it. And sometimes if we really just can't do it, it may lead to a future option on the unit. You never know.
Okay. Great. Well, that's what's going on under the hood, Steve. That's how we're able to tackle these really wild requests that come in from time to time. And thank you for that summary. I'm going to move on to the next slide. And this is an ordering chart that sits on our website, but it also gives a quick summary of the different options and example of how to set up your model number so you get exactly what you need. I'll run through it real fast. Obviously, the model and the channels are the first 5 characters. So you have 4 or 8 channel options on the 577. The next 4 series of this guy right here, here, and here are your 2 or 4 banks of channels. And you can go ahead and pick the AT20, which is the standard. I guess it is 20 volts. You were right. I thought it was 10. It's 20 volts adjustable.
Try to keep track with the different units.
Yeah, but that's better. I'd rather under promise and over deliver, right?
Absolutely.
Then of course, if you want to upgrade to one of the higher voltage options, you would use the AT35 or AT45. And If you want to upgrade to the optical outputs, you use the L82 or the L130. And if you're looking for the impedance matching, you use the TZ50 or the TZ35. The third item is the inputs, and we talked a little bit about dual triggers and also the optical inputs. And if you're just going with standard electrical inputs, the IA15 is your standard, which is right here. I got to get a sharper. I feel like I'm working with a crayon, a big Crayola. I need a sharper pen here.
All right.
And then the COM, of course, is the extra COM package, if that's something of interest. And then where are you in the world and what kind of power cord you need. So we'll try to give you something so you don't have to cut the end of the cord off and put your own connector on, or go out and buy another cord once you receive your product. So so the example here is down below. You can see a couple of examples. And here is one more example, the 8-channel AT20, AT45, TZ35, L130. Again, the optical outputs would have ST connectors. And then the dual trigger down at the bottom, DT15. The COM port is here, and this would be a US power cord. So anything to add on those two slides, Steve?
I think that pretty much summarizes it. Just again, noting that all your channels are grouped in a bank A and B and sort of side by side. So, and I think this does a good job of showing how different you could make this thing in terms of selecting different modules at each of those banks.
Takes a little time on the front end, but you end up with the product that really is adapted to your application. Good. So we'll jump in the Q&A. A couple closing remarks, though. We do have an online academy, and these are courses online that are free. They talk about the principles of timing and the terminology behind, jitter and rise time and overshoot and ringing, those kind of concepts. We have a few other on-demand webinars that might be of interest to you. There's our YouTube channel, which is loaded up with all kinds of videos about products. And then on our website, there's a little box that says Engineer Chat, and that's a live chat from 6 to 6 Pacific time, where you can talk to one of our application engineers and just ask a couple of questions. I will mention also there's kind of a fun YouTube video on our website. It's this one here on the right. Let me go ahead and add my marker here. This guy right here. We have a customer who spent like 2 hours reviewing the product, like every single little nuance about the product that you can think of. And it's not all perfect, but it's just a very good overview. So if you have more, if you're still interested in this product and you want more details about all, every feature, every function, this is the video to go watch. There's an index which links to every point along the way of the video, and literally from unboxing the product to the manual to going through each feature, each setup. It's a great video. I recommend that if you're still looking for more information. Great. So that being said, we've got some attendees here with some questions in the chat box. So I'm going to switch over to Q&A.